Lesson number 2, graphing motion. Let's take a look at the different types of motion graphs. Our first graph is position versus time. And let's take a look at specifically the slope of this graph. So let's label our axes. Below, our y-axis will be position, and that's measured in meters. And our x-axis will be time, and that's going to be measured in seconds. Let's apply our definition of slope, which is rise over run. Well, here the rise of our graph is measured in position, or change in position. The run for our graph is measured in time, so we'll put change in time there for the run. Now, what's defined as change in position over time? Well, that's our definition of velocity. So whatever the slope does, the velocity does. So here our slope will tell us about the velocity. So if we have a slope that's constant here, then that would show that our velocity is constant as well. So again, whatever our slope is doing is going to be what our velocity is doing. Here's our second type of motion graph, velocity versus time. So let's label our axes and apply the definition of slope here. So here our y-axis will be a measurement of our velocity in meters per second. And again, our x-axis will be a measure of time, and that's going to be in seconds. So let's apply a definition of slope. The rise of our graph now is in velocity, or change in velocity here. Our run is for time, or change in time. Well, by definition, change in velocity over change in time is acceleration. So for a velocity versus time graph, whatever the slope does, the acceleration does. So if you saw a constant slope on our velocity time graph, that would tell us that our acceleration is constant. So here the slope tells us about acceleration. Let's take a look at the motion of Usain Bolt as he runs at a constant velocity. Ready, set, go. Running, 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 running. Okay, if you remember, the slope of a position time graph tells you about velocity. So since his velocity was constant, we would need to draw a line of constant slope. So I'd write right on the graph that this shows that he's running at a constant velocity. Well, if we look at the velocity time graph, we choose the velocity he was running at, maybe here. Well, he maintained that same velocity the entire time. So that velocity will be constant. If you remember, the slope of a velocity time graph is acceleration, and his acceleration rate was 0 since he never changed his velocity. Well, this is also a slope of 0, which would mean the acceleration rate is 0. Now let's look at accelerated motion for Usain Bolt. Ready, set, go. Go, 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 go. Great. So here we can see that he accelerated and his velocity was increasing. So remember, the slope of a position time graph tells you about velocity. So if the velocity is increasing, the slope must be increasing. So if we start off with a low slope and go to a steeper slope and a steeper slope and a steeper slope and a steeper slope, we can see that as that slope increases, his velocity increases. So this shows a positive acceleration here. Let's look at the velocity time graph. Remember, the slope on a velocity time graph tells you about acceleration. So whatever the acceleration does, the slope does. So since we have a constant acceleration, we would show a line of a constant slope. Again, positive acceleration here. Now notice, these two graphs look different. Our position time graph has a changing slope. Our velocity time graph has a constant slope. But both graphs tell you that he accelerated. Finally, let's look at decelerated motion. So here we have to assume that Usain Bolt is already running, and that he crosses the finish line, he comes to a stop. So here again, recall that slope of a position time graph tells you about velocity. Well, if he's already traveling at a certain velocity here, say this velocity, his velocity needs to decrease. So we also need to decrease our slope. So our slope needs to get shallower and shallower and shallower and shallower. For a velocity time graph, recall the slope tells you about acceleration. Well, here we see that he had a negative acceleration rate. So we would need to show from a certain velocity he was running at, maybe here, his velocity would steadily decrease. Thus the slope here would show a negative acceleration rate. So again, if we look at both of these graphs here, our position time graph looks different from our velocity time graph, but they both tell you that he negatively accelerated and slowed down. This last section is for honors physics students. So we've talked about position time graphs and velocity time graphs, but what about acceleration time graphs? Well, keep in mind that all the motion we'll be talking about is motion of constant acceleration. Whether that's a positive constant acceleration, a negative constant acceleration, or a constant acceleration of 0, which would mean a constant velocity. So we won't see any slopes on our acceleration time graphs because we won't have any changing accelerations. But what we will have is this. Here we'll have positive accelerations, and we can graph below the axis where we'll have negative accelerations. So if we think about Usain Bolt's running the 100-meter race, he would start off out of the blocks and have a positive acceleration rate for a little while, and then he would get up in his running form and run at a constant velocity and have a 0 acceleration for a while, and then as he crosses the finish line, he'd have a negative acceleration rate. So this graph would show a positive acceleration rate, an acceleration of 0, meaning constant velocity, and then a negative acceleration rate. Thank you for watching, and see you in class.